Welcome to the first of 5 videos covering straight line theory at higher maths. This first video is going to focus on gradient. This will be a mix of both gradient theory that you should be familiar with from the National 5 course and new kind of concepts within that are considered the higher material. Both of which will be used throughout your course, through your exam, so be prepared to use any of the concepts discussed in the following video. Well, learning intentions. The first lesson intentions, I want to do a quick recap on how you calculate gradient using coordinates. Now, we can calculate the gradient of a straight line using coordinates. The formula used comes along based on the following kind of concepts. If you accept that gradient is the vertical change divided by the horizontal, if we take two coordinates, x1, y1, x2, y2, we can find the gradient of that blue line by looking at the coordinates and finding the vertical change and finding the horizontal. Well, our vertical change is given by the difference between y2 minus y1 and x2 minus x1 for the horizontal. Subbing them into the formula should lead to the familiar formula from National 5 of calculating gradient by doing y2 minus y1 divided by x2 minus x1. We shorten gradient to m, and this is a standard formula that I'm telling you now you will use a lot within your higher course, so please be familiar with it. Key things is this formula will work for any two sets of coordinates that join the straight line you're trying to find the gradient for. But remember, it only works for straight line. We will cover ways and means of finding the gradient of a curve at a particular point, but that is another branch of mathematics. Please do not be tempted to use this formula to achieve that goal. So, calculate gradient for line CD. This is a wee example for you to try. At this point, I'm going to use coordinate C and coordinate D, but you're free to pick any that lie in the red line. But I'm going to use 1, 4, and 4 minus 2. Key thing is, for these coordinates, whichever one you label 1 doesn't matter, whichever one you label 2 doesn't, as long as you're consistent in your choice of, if you've chosen 1, 4 to be the second coordinate, the x2 must be 1 and the y2 must be 4. You can't have the x2 being 1 and the y2 being minus 2 in the other coordinate. That doesn't work. The gradient formula will fail if you do that. So keeping 1, 4 as our first coordinate and 4 minus 2 as our second, you use the formula. Now notice MCD is a wee subscript CD. That's a good habit to get into when naming gradients. Call them by the letters that are joining the 2 points in which you're trying to find the gradient, because you're likely to do a question where you might be finding 2, 3, 4 different gradients within a bigger context question. And if you don't label them, it might therefore be hard for you to follow which gradient is which. So getting good habits now should make life easier when you're doing exam level questions. Subbing the coordinates in, again, watch out for double negatives, watch out for a negative taking away another negative, therefore becoming more negative. These are the kind of common errors that I still see with very able pupils making them, that then means their gradient or equation of the line is wrong, which can have, consequences for further down, especially if a question has, got a part B or part C. This one works out to be minus 2. Now, this is a key kind of point to make. Always use any sketches. You're likely to be given a sketch or diagram, certainly in the right context within your exam paper. Use the diagram as a guide to make sure your answer or your gradient makes sense to the diagram. I can see C to D slopes down left to right. Therefore, I should know from my basic gradient theory from National 5 that the gradient must be negative. Your formula, your y2 minus y1, must give a negative if the coordinates have been subbed in correctly. Another 2 examples for you to try. First example, I purely do use the formula as normal, but to understand that at higher, a lot of your gradients are likely to be fractional, that you're going to end up with fractions as the gradient instead of nice whole numbers. So be prepared to use fractions and be prepared to use them quite often at higher. Example 3 is slightly more complicated. It's not actually asking you to find the gradient, it's asking you to use the gradient to find a missing coordinate. What we do is we sub all the values in, including our gradient for the left-hand side, and then we have to rearrange to make P the subject. Watch out, the double negative, minus 2 becomes positive 2. If you miss that, that can obviously change your answer for P, which will therefore have consequences if you're then going on to use the coordinate D for something else. Doing the work, you should have got P equaling 10. Gradient, horizontal, vertical lines. They're the kind of the odd ones out within the kind of gradient family, is that they don't quite follow what the rest of them do. They're special cases. So if you have a horizontal gradient, it will always be 0. It will have a 0 value and that is an indicator that you have a horizontal line. So if you calculate gradient, you get 0. That's your proof that you have a horizontal line. Or if they tell you the line is horizontal, you know the gradient is 0. Vertical lines are different. They're undefined, basically infinite, but we use the word undefined to prove those. If you get a scenario where you're going to get an infinite answer, which will 9 times out of 10 be you're dividing by 0, therefore you have an undefined gradient, and therefore you have a vertical gradient, and therefore a vertical line. We use these facts within questions depending on the context being asked. Just to prove it works using the coordinates and using the formula, if you take line AB and line CD, you can clearly see from the diagram one's vertical, one's horizontal. But subbing 2 coordinates in for the vertical line AB, you will find that you will end up with a division by 0. Mentioned it in the previous slide. For undefined vertical lines, you'll end up with the denominator being 0, and that's what leads to your answer being undefined. Doing the opposite for the horizontal, using 2 coordinates from the line CD, when you sub them in, it will be the numerator in the formula that ends up being 0, and that's what leads to the 0 gradient. So denominator 0, you have an undefined gradient. Numerator 0, you have a 0 gradient, therefore a horizontal line. And these facts can be used, again, within bigger context questions. Next, learning intention. I want you to understand why gradient can be found using tan theta and be able to use it successfully to find the gradient of an angle of a line. This is new material. This may have been covered by your teacher at National 5, maybe as extension, but this is considered higher level, and therefore is relatively likely to appear at some point, certainly within your higher exam. Not guaranteed, but there's a good chance. So, proof of why tan theta can be used for gradient. If I use SOHCAHTOA for a right angle triangle, we know that tan theta is your opposite over adjacent. Okay, but we also know that gradient is your, vertical change over horizontal. Well, between 2 coordinates, you will always create a right angle triangle. Therefore, from the diagram you can see in yellow there, your opposite will always be your vertical change and your horizontal, your adjacent. That leads to the gradient being opposite over adjacent, which in turn means we can replace that by tan theta. So if we take the angle made in the positive direction of the x-axis, sub that in, do the tan of that, that will give you the gradient of the, the straight line that you're trying to find. Again, this is an important fact. You're not given. You need to walk into your exam remembering this, and it allows you to either calculate either the gradient when the coordinates aren't known but the angle is, or the angle a line makes with the horizontal, which can be relevant, once again, to questions that involve more. A couple of key bits to understand here. When the line is sloping down the way, your value of theta will be greater than 90. We still use tan theta. You sub an angle bigger than 90. What will happen is that the calculator will print out a negative gradient, as you would expect, because once it goes beyond 90 theta, you have a line that's sloping downwards, therefore it will be a gradient sloping downwards. Remember, you must always use the angle created with the positive direction of the x-axis. If you don't, you will then be using an angle less than 90, and therefore you won't get a negative gradient, as you should in this scenario, because the line does have a negative gradient. And remember, for negative gradients, if you look at your diagram, you know the gradient is negative. You therefore will know the angle must be bigger than 90. Again, if you're asked to calculate it, that will be important. And we will cover a couple of examples of that next. So, a couple of examples to try. Example 1, find the gradient of the line AB. Well, we're just going to simply use tan theta. This is an example, throw it in. You get 1 over root 3, or if you've got the good Casios, the calculator will probably throw root 3 over 3, where they've rationalized the denominator. Or in this scenario, if there's no specification, you could throw the decimal version in. I would prefer you to get in the habit of using exact values. It is better, but if the question doesn't ask, you are free to at least give some semblance of a decimal answer. But try and go to a few decimal places so you don't introduce too big a rounding error. Example 2, this one's slightly more different, and this one's their challenge you. They actually want you to find the angle instead of the gradient. So find the angle the line PQ makes with the positive direction of the x-axis given the coordinates P equals 5 minus 4 and Q minus 1, 2. Again, if for some reason the question in the exam didn't give you it, draw a wee sketch of your own. It's good for giving you a guide on what's going on. From plotting P and Q, I can see that I'm going to have a negative gradient. I've been given 2 coordinates, therefore I can work out the gradient. And since the gradient's negative, I know my theta is going to be bigger than 90. So this question is going to involve a wee bit of National 5 theory in order to be able to work out the angle. Well, calculating the angle using the coordinates, I get quite rightly a gradient that's negative and it's minus 1, which kind of fits the slope of the rough sketch that I've done. Now, tan theta equals -1. Where have we seen a scenario like this before? Well, hopefully you're all screaming that we've seen this either in our, solving trig equations, or even going further back, you could have solved tan theta, wouldn't have equaled -1, but you would have done some version of finding the angle with SOHCAHTOA. But the -1 was relevant. We introduced you to the concept that we don't do the inverse tan of a negative, but we take account of any negatives in the cast diagram. Now, for this context, we don't need to use a full cast diagram, even though we know, all is positive between 0 and 90, sine is positive between 90 and 180, which makes cos and tan negative. Tan is positive between 180 and 270, which means sine and cos are negative in that quadrant. And cos is positive between 270 and 360, which makes tan and sine negative. But the context, your angle will only ever be between 0 and 180 for finding the angle a line is making. So we can ignore the tan and cos quadrants and focus purely on the all and sine. Well, given that we're not wanting it where it's positive, tan is negative in the sine quadrant, therefore we are looking for 180 minus 45, the angle would be 135. So within a gradient question, we're having to use our concepts and understanding of, solving trig equation theory, which is important because, again, at higher, we start layering all the different theories and maybe use them in a bigger context. So you've got to be comfortable using these wee skills. Example 3, taken from the 2012 higher paper 1, question 4. Higher paper 1 was multiple choice back in 2012, but I've got rid of the multiple choice because your exam will not be multiple choice, and I'd like you to work this out. Now, given this question was non-calculator, I'm throwing this in before I've really kind of covered trig theory within the higher course, but some of this should be understandable if your class teacher's covered it, or once you watch this video later down the line, once we've recapped and gone further with trig, you'll understand how to do this without a calculator. We are being asked to find the tan of 150. Now, non-calculator paper, so we've got to use our understanding of trig and the cast diagram to answer. From our cast diagram, you can see that tan 150 is therefore an angle in the sine quadrant. So tan, the answer to that would be negative because tan is negative between 90 and 180. So we know that. Now, what we can do is that we need to relate the tan of what we're doing back to between 0 and 90 because we can use the exact value triangles if we have an angle. And every quadrant within those 4 quadrants always relates to the first quadrant. So we work back and realize that the gradient is negative, so we throw in a negative, but it's the same as doing the negative of tan 30. That would be the same answer as doing tan 150, because to get to 150 in the cast diagram, we would have done 180 minus our related angle, but that's what we want. So for 180 minus related angle to be 150, our related angle had to be 30. Using our exact value triangle, first one comes from a 2 by 2 by 2 equilateral triangle. When you do that, you find that the tan of 30 is opposite over adjacent, so it's 1 over root 3. But again, if they did ask if it rationalized, you could give it as minus 1 over root 3. And if they asked to rationalize it, it can be minus root 3 over 3. Again, this will be covered in more detail once you're further into the course, particularly once we've covered the trig concepts and the exact value triangle for non-calculator. Next bit I want to do is a recap on parallel lines and gradient. Key concept, because if they mention parallel lines, they're mentioning something important about gradient. If a line is parallel to another, they will both have the same gradient. That is a mathematical fact, and if that is mentioned, whether it be via diagram, whether it be via words as part of your question, they're telling you the gradients are the same, and therefore we can use that fact. So always look out for those kind of what I call triggers to get you into that mindset of, right, the gradients are the same, I can use the same gradient. Just to prove the point, here are 2 lines, EF and GH, which are parallel. If I find the gradient using the gradient formula, I find that EF has a gradient minus 3, as expected, because it's sloping down and looks relatively steep. And then if I put G and H through the same gradient formula, it turns out I have minus 3 as well. Therefore, since the gradients are the same, I can make a statement saying, since the gradients of lines EF and GH are the same, they are parallel. So I've proven what I've been asked in example 1. Example 2 for you to try. Right, to prove ABC is a vertex, I would first of all do a wee diagram again to get an idea of what's going on. So if it's asking to show it's a parallelogram, my diagram has thankfully kind of come out looking at a parallelogram. I need to prove that opposite sides are parallel. That means I'm going to work out 4 sets of gradient here. If I do A to B, I work out it's got a gradient of minus 5 over 0. From my diagram, I did get a suspicion that I could end up with a vertical gradient. I do. It's undefined. Doing the same for DC, for CD, sorry. You sub them in, you also get 5 divided by 0. Irrelevant that the minus 5 and one was positive 5. What we're saying is that it's undefined. Therefore, we have a vertical gradient. Again, thus proving MAB and MCD are parallel. Doing the same for MDA, 7 in the coordinates. I shouldn't get horizontal vertical here. I should get a gradient. When I do, I get 2, 6. Now, you could simplify that to 1/3. I haven't given them try to squeeze this all into one space. All I'm trying to do is prove they're the same. Therefore, 2, 6 for CB is the same as the 2, 6 for DA. As again, if you're doing a question that's wanting the gradient as part of the answer, always put it in the simplest form. Here, my question is asking me to prove they're the same, so I can say that 2, 6 is the same as 2, 6 without the need to simplify. But good habits, I probably would simplify if I'd had more space. Finally, make a statement. Since MAB equals MCD and MDA equals MCB, quadrilateral ABCD is therefore a parallelogram. Third example for you to try, but this time instead of proving, it's asking us to find a value of one of the coordinates. Since they've told us it's a parallelogram, that is a fact that we can use, that we know that gradients are the same. But to help us understand what gradients are the same, draw the diagram. I've roughly guessed where S is in this in order to make it a parallelogram. Since it's a parallelogram, PQ and SR must have the same gradient, and the same is also true of PS and QR. So I'm going to use that fact in order to find K. So if I find PQ, I find it to be minus 1 over 7. I can then use the fact that MPQ must be the same as MSR because they're parallel. Therefore, subbing all of this in MSR and replacing the left-hand side with minus 1 over 7, because we know the gradient due to the parallelogram and those lines being parallel, I get, again, just like the similar question earlier, I get an unknown of K. I just need to rearrange and solve. Again, watch out for your negatives. But this time, when you solve it through, you should have got a value for K of minus 1. So the coordinate of S was minus 2, minus 1. But all you were asked to find was the value of K. Collinear. I want you to understand what collinear means and be able to successfully prove points are collinear. This is, again, a higher level topic, so could play its part in your exam next May. 3 or more points are said to be collinear if they all lie in the same straight line. Okay, to prove collinearity, we must show that the gradients from a common point to all other points are the same. Okay, so if I give an example, prove that the following points P, Q, and R are the collinear. First of all, I'd find PQ. Now you're free to pick. I'm going to pick PQ and PR, but you could do PQ and QR. As long as you have a common point for both, then then it's suitable for you to have done or used it to find the gradient. So finding PQ, I find that the gradient of that is 1/3. I then go and do the gradient of PR. As I said, I'm going to make my common point P, but it doesn't have to be P. It can be any of the letters. So I could have done PQ, PR, which is what I've done. I could do PQ, QR in order to find that, and I can do PR, QR. So there's different options as long as there is a common point. Find the gradient of this one. Thankfully, it also turns out for 1/3 because I need that to be the case for collinearity. Then I would make a statement. Since PQ and PR have equal gradients and a common point, P, then P, Q, and R must be collinear. That statement needs to include reference to the equal gradients, reference to the common point, before you then state that it's collinear. Now, you must make a statement like that if the question asks prove. Key point to understand, I've put it up there in the purple box, but collinearity is more likely to appear as a vectors question than a straight line in the exam. It can come as a straight line gradients question, but it's more likely to come in vectors. So therefore, once we've covered that topic, you'll understand how to do it by using vectors instead of just straight line. Last area of gradient is I want you to understand the key facts about gradient and perpendicular lines. Again, this is a higher concept, so is likely, near on certain, to play some part in some question within your higher exam, maybe more than one question. I'd actually suspect it would be more than one in your exam. So this is a key concept to understand. Now, if I take a line OA and then take, the line OB, which is 90 degrees to it, the gradient of OA is 1, and the gradient of OB turns out to be -1 using the gradient formulas. If I take a second line OA, this time draw a perpendicular line OB, I can see that OA is a gradient of 1/2, and B turns out to have a gradient of -2. Some of you may be starting to spot what the pattern is in regards to perpendicular gradients, but let's take some more examples. If I take a new OA, that has a gradient of -1/4, sorry, it's sloping down, and OB, which is a gradient of +4. Taking another two sets of perpendicular lines, OA and OB, OA would have a gradient of -5/2, sloping down, and OB would have a gradient of 2/5, which is quite straightforward because it's a gently sloping upward line. And taking the last set, if I take an OA and the OB perpendicular to each other, OA has a gradient of 5, quite steep, positive gradient, and OB has a negative but quite gentle 1/5. Can you spot any connections between the gradients of perpendicular lines? Well, what turns out to be the case is if you multiply the gradients of two perpendicular lines, the answer to that multiplication will always be -1. That is a mathematical fact, and is a fact that's going to allow us to do a lot of work within higher. So the note I would like people to have is two lines with gradients m1 and m2 are perpendicular at exactly 90 degrees to each other if gradient 1 times gradient 2 equals -1. As I said, very important fact that must be written down if used to find a perpendicular gradient. When you know two lines are perpendicular and you know one gradient, you can calculate the other using the rearrangement of the formula to find that m2 would be -1 divided by m1. Now, subbing that number into the formula, it's not necessary, isn't actually necessary, and there is a quick way of doing it. If there's a mark available for the gradient, it's not for using the formula, it's just for getting the perpendicular gradient correct. If I give you a gradient of m1 equals 3, well, the perpendicular gradient would just be flip the 3 to become the fraction 1/3 and change its sign, so it becomes -1/3. For one that's already a fraction, so if m1 was -2/5, you flip the fraction, so it becomes 5/2, and you change the sign, so it becomes +5/2. And that's the quick method. It's certainly the method I use, but I do make reference to m1 times m2 equals -1 in my question to show how I understand where the perpendicular gradient comes from. Some examples to try. Since line AB has a gradient 7, line CD is perpendicular to that line AB. What is the gradient of line CD? Well, using the proper formula, I would divide the 7 across. It comes out as -1/7. But like I said personally, if MAB is 7, you just simply make it negative and make it a fraction with 7 on the bottom and 1 on the top. So either method, you want to do either, feel free to do it, but I personally just go to the flipping it and making it negative, but make sure you make reference to the m1 times m2 equals -1. For example 2, I need to show the four vertices of a kite and show that the diagonals of the kite are perpendicular. Again, if a diagram's not given, draw it so you get an idea. The diagonals of the kite are AC and DB, so therefore I've got to prove they're perpendicular. So therefore, if I can prove their gradients and prove the gradients are perpendicular, that will be my proof needed to show. So finding AC using the coordinates given, I find that it's got a gradient of -3, as expected from my diagram. It's sloping downwards and seems relatively steep. BD is positive, sloping upwards. So when I sub in the values, I should get a positive gradient, and it's got quite a low value of gradient at 1/3. I can then do my proof by showing that when I times these two numbers together, I get -1. That's allowing me to make a statement because it's a show question. Since MAC times MBD equals -1, diagonals AC and BD must be perpendicular.